Today, I want to show that quantum computing can actually offer an advantage over classical computing in solving certain problems. This video is not about how a quantum computer works in detail. Instead, it's aimed at people who are just getting into the topic or even complete beginners who are simply curious about why quantum computing is often seen as so promising compared to classical computing. The goal is to demonstrate both mathematically and intuitively why quantum computing can outperform classical approaches for specific tasks. You don't need to understand how a quantum computer works to follow along. No special background knowledge is required, and the content is structured in a way that should be understandable on its own. That said, if you have zero background in physics or electrical engineering, it might be a bit harder to follow every detail, but I keep things simple and clear throughout, and whenever something comes up that's not really common knowledge, I'll include a link below to IBM's official tutorials, so you can explore that on their website or YouTube channel if you're curious. Now, how is the video structured? First, I walk through the basic theory, what the problem is, and how we'd normally solve it using a classical computer. And second, I'll introduce the Deutsch-Jozsa algorithm, often called the hello world of quantum computing, and show mathematically why it gives us a speed up in this particular case. Finally, I will demonstrate that it actually works by running the algorithm on IBM's Qiskit platform using a quantum simulator. Let's now walk through the actual setup we will use to demonstrate this advantage, specifically using the Deutsch-Jozsa algorithm. I keep the explanation very basic so that anyone can follow along. And if you already know what inputs and outputs are or how a mathematical function works, some of this might seem obvious, but I want to make sure everyone can follow. So first we start with an input, and that input is a bit string. What does that mean? A bit string is simply a sequence of zeros and ones. For example, 0, 0, 0, 1, 1, 0, or 1, 1. This represents our input to the system. Now, to visualize it more practically, imagine light switches. Each switch can be either on or off, just like a bit can be 0 or 1. So if you have two light switches, if both are off, that corresponds to 0, 0. If both are on, that's 1, 1. If the first is on and the second is off, you get 1, 0, and if the first is off and the second is on, you get 0, 1. This is exactly what we're working with. Combinations of bits, which you can imagine like switches in different on-off states. So if you have two switches or two bits, we get four combinations. That's our input space. 0, 0, 0, 1, 1, 0, and 1, 1. Of course, you could have more bits. Three switches would mean 8 combinations, and so on. But for now, let's keep it at 2. Now we have a function which we can call f of x. This is just like any function you know from math. It takes an input and returns an output. In our case, the input is not a single number like x equals 2, but instead the bit string. For example, x equals 0, 1. Still, the idea is the same. You give the function input, and it gives you back either a 0 or a 1. That's it. So you can imagine something like this. You pass in 0, 0, and the function gives you back 0. You pass in 0, 1, and maybe it gives back 1. You pass in 1, 0, and it gives back 1, and you pass in 1, 1, and it gives back 0, and so on. What the function does internally with the bit string, we don't know. That's hidden. We just call it a black box. You give it an input, and it returns either 0 or 1. Nothing else. These are the only two possible outputs. So again, to summarize, the input is a bit string, a combination of zeros and ones. The function does something unknown to us with this input, and the output is always either 0 or 1. Only those two values are allowed. In this example, we are using n equals 2, meaning we are working with 2 bits. So our possible inputs are 0, 0, 0, 1, 1, 0, and 1, 1. We send each of these into the black box, and for each one, the black box gives us back either a 0 or a 1. That's the full setup for now. So what does the function f of x actually do? Well, the important thing to understand is we don't know exactly what this function is doing internally. It also doesn't matter. First of all, I don't know what it does either. It's irrelevant what happens inside. What matters is what the output looks like. That's the only thing we care about. Now, this function can behave in 3 different ways, and we will go through them one by one. Let's say the function is fixed. The system is set, the function has been selected, and now we start feeding it inputs. For example, we first send in 0, 0 as our input, and the output is 0. We then send in 0, 1. Again, the output is 0. We continue with 1, 0. Again, the output is 0. And finally, we try 1, 1, and again, we get 0. So no matter what input we give, the output is always 0. That's the first case. The second case is similar, but this time, instead of always getting 0, we get 1 every time. We send in 0, 0, we get 1. We send in 0, 1, we get 1. 1, 0, 1, 1, 1, 1. So again, for every input, the output is exactly the same, just always 1 instead of 0. Both of these are examples of the function being constant, meaning that the output never changes, no matter what we put in. Now comes the third possibility. The function still returns either a 0 or a 1, but this time exactly 50% of the inputs return 0 and the other 50% return 1. So for example, 0, 0 returns 0, 0, 1 returns 0, but 1, 0 returns 1, and 1, 1 returns 1. So the function splits its outputs evenly. For half the possible inputs, it gives 0, and for the other half, it gives 1. And these are the only 3 possible cases we are considering. Just to make it 100% clear, we are talking about 3 different functions here. Each time we activate the black box, it randomly selects one of those 3 functions. That means either the output is always 0, or the output is always 1, or it's exactly 50-50 between zeros and ones. Once the function is selected, it stays fixed. We can feed it as many inputs as we want. It will always give us the same output pattern. Then if we want, we can reset the box, and it will randomly choose another one of the 3 functions again. And we can test it again and again, and so on. And here's the key thing. There are no other possibilities. The functions cannot behave in a way where, for example, 70% of the outputs are 1 and 30% are 0. That's not allowed. The black box is designed in such a way that only 3 output patterns are possible. Always 0, always 1, or exactly 50-50. Now to give names to these behaviors, if the output is always the same, whether it's always 0 or always 1, we will call the function constant. If the output is exactly 50% 0 and 50% 1, we call the function balanced. So even though we technically have 3 possible functions, one that's always 0, one that's always 1, and one that's balanced, we group the first 2 together and call them both constant. So in the end, we're distinguishing between just 2 categories. The function is either constant or it is balanced. And now you see a little example. If we have the input 0, 0, we get 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 0. So this is a constant function. And the second example, we again have 0, 0 and 0, 1, 1, 0 and 1, 1, and we get 0, 0 and 1, 1. So this is a balanced function. So what is the goal here? Our goal is to figure out whether the function is balanced or constant. Once again, we do not know which function is currently active inside the black box. All we can do is send inputs into the black box and read the outputs that come back. That's it. That's it. We do not get to look inside. We cannot see how the function works internally. All we can do is test it. Now, if we send in one input and look at one output, that obviously tells us nothing. Because if we only try one case, we have no idea whether the function is balanced or constant. We just have one data point, and that's not enough. So let's go back to the setup we had earlier. We are working with inputs that are bit strings, and each bit can be either 0 or 1. And if we have n bits, then we can build up all possible combinations by using the rule 2 to the power of n. So, for example, if n equals 2, meaning we have 2 bits, then we have 2 to the power of 2 equals 4 possible inputs. That gives us 0, 0, 0, 1, 1, 0, and 1, 1. 4 combinations in total. If we had 3 bits instead, so n equals 3, then we'd have 2 to the power of 3 equals 8. That would give us 8 combinations, for example, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. You can try it yourself and write them all down. It always works this way. But here's the key point. We don't know anything about the function, and all we can do is to send inputs and record the outputs. That means the only way to figure out if the function is constant or balanced is through trying. We have to try inputs one after the other and write down the output we get. And only after a certain number of tests, we can confidently say this function is constant or this function is balanced. Let me give you a concrete example again, just to make it clearer. We have the black box where a function f of x lives. It takes 2 inputs and returns 1 output, all of which are either 0 or 1. In this case, we are working with 2 inputs, so again, n equals 2. That gives us 4 possible combinations, 0, 0, 0, 1, 1, 0, and 1, 1. Now we activate the black box, meaning it randomly selects one of the 3 possible functions, either always 0 or always 1 or balanced, meaning 50% 0, 50% 1. That function is now fixed. Then we start testing inputs. We send in 0, 0, and the output is 0. We send in 0, 1, and the output is again 0. We send in 1, 0, again 0, and finally 1, 1, still 0. So we can now clearly see the function is constant and it always outputs 0, no matter what we put in. Now we'll do it again. We send in the input 0, 0, and we get an output of 0. Then we send in 0, 1, and now we get an output of 1. Now, if we think about it for a second, it's already clear that the function must be balanced. Why? Because the function is only allowed to behave in 3 ways. It can return only 0, only 1, or exactly 50% 0 and 50% 1. If we have already seen both outcomes, 0 and 1, then there is no way that the function could be constant. It cannot return only 0 or only 1 anymore. We've already seen both, so it must be balanced. In this case, we figured it out after just testing 2 inputs. That's only 50% of all possible inputs. So sometimes we are lucky and can figure it out early. So let's try it again. We reset the black box and let it randomly choose a new function. Now we send in 0, 0 and get 0, then 0, 1 and again get 0. But now at this point, we don't yet know if the function is constant or balanced, because could still go either way. If we now test the input 1, 0, and it gives us 1, then we immediately know the function must be balanced, because we've seen 2 zeros and 1, 1, and if 1, 0 gives a 1, then the remaining input, 1, 1, must also be 1. Otherwise, the distribution won't be exactly 50-50. But if 1, 0 gives us another 1, then we would have 3 zeros and only one input left. In that case, we know it can't be balanced anymore, so the function must be constant. So just by testing 1, 0, we can now definitely say whether the function is constant or balanced. So let's summarize all of this. In our simple example, we had only 4 possible inputs, but the logic applies to any number of inputs. Even if we had 8, 16 or more inputs, the rule stays the same. To be absolutely certain whether the function is balanced or constant, we need to test half of all inputs plus one more. Mathematically, here's how that works. The total number of possible inputs is 2 to the power of n. That's because each of the n bits can be either 0 or 1, so we have 2 to the power n combinations. 50% of that is 2 to the power of n times 0.5, or just 2 to the power of n minus 1. And 50% plus 1 is 2 to the power of n minus 1 plus 1. So that's the maximum number of input-output tests we need to run to be absolutely sure whether the function is constant or balanced. And we can only do that by checking input after input one at a time. Now, of course, sometimes we might get lucky and figure it out earlier, like in the first example, but in the worst case, we need to check 2 to the power of n minus 1 plus 1 different inputs. And for large values of n, that can take a lot of time. And this is where quantum computing, and specifically the Deutsch-Jozsa algorithm, comes into play. Instead of checking one input at a time, up to potentially exponential amounts of work, a quantum computer using the Deutsch-Jozsa algorithm can figure out whether the function is constant or balanced with just a single query.